software, but we kind of have to provide requirements to flight software for what our functionality needs to be. And I kind of go through the process that we've been using for SLS the past 6 years, 7 years or so, and how we approach it. So over here is a lot of my co-authors, and there's some of the bigger leads across the SLS GNC. This work, though, goes across flight software, SLS, GNC, system engineering, M&FM. So there's a lot more people than just ones who are on here. And this effort's been going on for 8 years or so when we first did this study that led to how we're doing this now. So I have to make sure I account for a lot of people have contributed to this work over the years. So I kind of go through top-level GNC requirements, what our functional requirements look like, how we break it down into what our model-based approach is for our architecture, requirements, flight software, kind of go through our simulation side, how we provide that to flight software, and some of the processes back and forth we use to verify quality, functionality, that kind of stuff. So at a high level, from GNC, our high-level requirement is insert a payload into orbit with a given accuracy. So basically, we have orbital requirements, and we have to do this with a lot of caveats. So we have to do this safely, stably, be able to respond to abort conditions off nominal conditions and make sure the vehicle maintains stability, check for sensor health, quality, all that kind of stuff. But in the end, it's 3 metrics. How well are you in orbit to where you said you're going to go? So that's kind of our main metric that we have to always assess against in our simulations, and also that ties into when we do some of the SIL testing, incentive testing, we do hardware in the loop, how we compare back to what our results are, what our performance is from the GNC perspective. So from that, we have to go all the way from that vehicle spec down to our modeling simulation to the flight software and kind of full the whole loops to close our verification objectives. We kind of have to show that our sims work and also hardware works as well, and there's no unintended effects. So in terms of our GNC, just kind of quick overview what GNC is. Essentially, we take the input from the sensors, the RENU nav box, our rate sensors, the RGAs, and then our mission manager tells us what mode of flight we're in, what is our operational scenario, what kind of other health status kind of thing, and the abort conditions kind of thing. We feed it through our GNC block here. Basically, we have our nav, guidance, and controls, where basically we figure out where we're at, where we want to go, then how do we kind of get there. So all the way from reading in sensors out to our TVC, engine throttle, engine cutoff, those kind of commands to basically fly the vehicle. And we do a lot of Monte Carlo simulation with this, where we have this block here and implemented a big 6-off simulation, and we'll do Monte Carlo analysis to assess sensitivities, performance, all that kind of stuff to verify that the design for the sensors and our software here matches the requirements for the various scenarios. So in terms of how it's set up in terms of requirements-wise, so back in the days of Constellation, a lot of our work was all, the heritage method was all handwritten. We'd go off, do our analysis, design the algorithms, and then we'd write it down on paper and say, these are the requirements for the GNC flight software, hand them to the flight software guys, they would independently implement it, and then in the end we come back and we compare sims and make sure it all worked. That required a lot of paperwork, a lot of requirements, and we moved over from Constellation to SLS, intentionally driven decision to kind of reduce requirements on our side. So like I said, we reduce our requirements that are high level from the vehicle side to that one insertion requirement instead of having a bunch of high level requirements. We still decompose it internally, but traceability wise, we have those high level metrics that we track to it. And so we've kind of reduced this to make it a little easier for management. So kind of from that vehicle side here, we have level 1 where you kind of have the integrated whole vehicle stack, and level 2 for an integrated vehicle where you might have the core stage, the upper stage, the human caps, all that kind of stuff. This is kind of where we sit here, because we're GNC of the core stage with its engines, its sensors, its structure, all that kind of stuff. And then you go down a level deeper and you hit here where you hit the sensors, some of the hardware pieces, elements. For GNC side, we do a lot with TVC, a lot with RENU, the RJ navigation sensors, make sure we understand what their software is, how they operate, and how that feeds into our performance analysis, and how we design our GNC algorithms. So that kind of goes into this design math model approach, where instead of capturing these things as requirements, we kind of capture them more so as models. And models in this sense might mean, for our nav sensor, it might be a software model of the RENU. Like this is a model of the RENU for performance that we validate against hardware. This may be a model of the FCOG selection algorithm. This may be a timing model. This may be a those kind of models take the place of requirements. So for our GNC system, our GNC will be a model of GNC instead of a bunch of shall statements that say implement this algorithm this way. It kind of because hey, here's a model, here's an implementation of it, and kind of go and place it that ways. We do a lot of physics-based modeling with the sim, so we have our 6-off sim here. We work with folks at Langley and other centers where we do shootouts a lot of the time to make sure that our simulations match theirs for our cross-verification results. And a lot of these parameters can go for requirements internally to us. So like some of our time-dependent parameters for data launch, so that kind of can be requirements to develop those variables for us. So in terms of how we're looking at GNC, so we have our little, basically our algorithm component block. And so this kind of started off when we were first starting the program as a way to say, instead of us writing down our requirements for GNC and describing it verbally, we wanted to be able to provide an executive model, because we do our analysis in a big 6-off sim in C. Our flight software guys write flight software in C. And so we are already kind of developing products that are very close to, but not flight software. We don't have a lot of the rigor in our testing, the rigor in the processes that our flight software group might have, but we do stuff that's dangerous enough to be flight software. So the idea was that take what we do and have this common model that captures our GNC algorithms that we can then use in our analysis tools in 6-off and feed it over to flight software, so that in the end, when we go off to our software in the loop and the actual vehicle, that same piece of algorithmic code that we've generated with inputs from flight software and everything else is executed across the board. So we have good tie-in from how we've done our analysis to how it's implemented to how it's flying, to kind of give full insight to what's going on here. And there's less risk of having an algorithm change because of the way it was written down. It kind of gives us a lot of good insight to how it works on all these different platforms. So part of our DMM for our GNC includes executive algorithm, so it includes C code, parameter definitions, what our parameter files are for like all our inputs, a memo that describes the algorithms and the approaches, interface assumptions, what kind of data we're expecting where. So from our side, from the nav, we're very concerned about what the sensors put out, so making sure that the ICDs from the sensors match what's being fed into the flight software, to the hardware managers, all that kind of stuff. So we kind of poke in little areas, make sure that things match what we expect them to do. And then our GNC model is pulled directly from our sim, allows us to tie back to our, every time we do a Monte Carlo simulation, we then tie it back to this code, had these results, so we can then do our own regression testing on our software to make sure it's still good, and also allows us, as we go into other comparisons, we can compare the Artemis framework with our solutions, with flight data eventually, and kind of compare across the board what we're doing. And so part of this process was to make sure we bring in the flight quality to us, because we don't do flight software code. We kind of developed the CR process, where we go from our algorithm design to our 6-off analysis to eventually our model. We feed it over to flight software. They do a code review. We bring them in early to review our algorithms for their awareness, maybe say, hey, this is better from a flight software perspective. This fits better in a real-time environment than what you're doing here. And kind of fitting those things in, and through a CR process, those come back to us, and then we remodel on our side, redo our analysis, and mirror that the traceability as we change the code, as it changes the performance for what we're really concerned about. This whole process goes back through flight software implementation, software in the loop, and flight software qual. And there's always this feedback to our model where we can accept changes and make improvements, correct for any hardware issues that we see, and revalidate our performance results from a 6-off perspective. So in terms of this process flow, we do a lot of CR and repos on both sides of it. On this side, we kind of have our modeling on the GNC side, where we have our repositories here, our simulations. We have our comments here, our other documentation here. Early on, we did this. We also had to know that we can't just develop code that kind of willy-nilly. So we tried to bring in some coding assumptions, bring in what coding standards we could in terms of naming conventions, just the typical things you would see, and have reviews with flight software, make sure we're doing things mostly in the right way. So that when we deliver it, it's all that stuff's kind of already taken care of. Similar to the way we do some like PPQ and RNA and kind of analysis, some static analysis before we deliver it, to make sure that we're kind of in the right direction, make sure we have a quality product going out. And then from that, the delivery of software, we sit inside of our GNC portion of here, and then from that testing area, you can get CRs back to us from that testing. Integrated flight testing gives us CRs back, and also testing our unit test cases. There's a lot of methods where, as assumptions we've made about how it runs on the hardware, we've had to iterate with that. There's a capability on these paths to go back to our design for them to be formally tracked for this. And as we do our various simulations, we can track our performance towards our high-level requirements as we go through all this. In terms of the actual process flow here, this kind of gets into more of the weeds, how we do this. So a lot of the standard flight software approach is still down here. A lot of the rigor in terms of your unit testing, the test cases, testing requirements is all still here. It's just kind of we plug in an element that's closer to what's needed in terms of the flight code implementation. So we go from our analysis process to develop an executable model that we can then deliver, taking in the coding standards, other inputs from flight software to drive how we implement the code. We develop algorithm test cases that say, as we develop this code, this is what it needs to do, this is the kind of performance we expect out of it, that goes along with it. So to our repo, we kind of track this stuff. And part of this too is we had to kind of formalize our processes a little bit more, especially as we get closer to flight code, flight algorithms, where we've hardened our CR process, our review process internally to make sure that everything is really traceable and has a lot of traceability and review before we release our models to flight software for implementation in flight. And then once we pass it over to the flight software group, then they do the flight code implementation, integration with the other drivers, on the flight platform. A confidence test where they make sure that our implementation here matches on their side. So we provide unit test cases as well for over whole flight. The data is then fed on their side to make sure it matches what we ran to make sure the implementation is correct. We then do the full unit testing and then the software integration, and we end up at this whole flight level test and hardware in the loop, where we then compare back to performance in their environment to performance in StickSoft to make sure that we meet our performance we need under hardware latencies, hardware comm effects, all those other kind of things that you weren't really able to model in a software environment. So in terms of these verification, we implemented this throughout the system at multiple levels to track, make sure that our code is doing what it's expected to do. So at our GNC level, through our CR tool, we track the changes to it. We do a lot of iteration and regression test cases, looking at our performance metrics across guidance dynamic control to make sure that we have understanding of our performance to our requirements. We do unit testing between Maverick releases, so as our base code changes, as our dynamics model changes, other flight inputs change, we have traceability so that we can say 5 versions ago, this is what the results were, they're still good, and as we make changes, we can see how the changes affect against our performance verification requirements. And then at the GNC model delivery, we then build a unit test case wrapped around that, basically from our simulation, take out the inputs from the sim, take the outputs of our GNC model, and then basically, when we pull out the GNC model, we run that test again with those same inputs and verify we get the same outputs for that level of unit testing. And then we saw some issues because we're doing a lot of analysis on a x86 platform and not on a PowerPC. So when we switch platforms, we also have a flight-like processor that we do this on as well. So we'll take our flight code, move it over to that other platform, recompile it, rerun our unit test cases for validation down the line so that we can identify as we switch platforms, these things change due to rounding errors or just due to numerical precision kind of things between platforms. That gives us good traceability back from our analysis on our cluster to flight hardware, and then to its implementation and on and so on and so on. Once that code is delivered to flight software, that same test is repeated, but now within a flight software architecture to make sure that we're still good on that side. And here, a lot of also our design level requirements, our software specifications kind of come into play, where we verify that the requirements for the code needs to do are written down, modeled, tested, validated for the flight quality and for the class day kind of software. And then at highest level here at the end, we get to the flight software system where we have integration modeling with all of the hardware DTUs, all the hardware simulators, where you can kind of come into play and say, now some of our models have changed, so instead of having software models of our sensors, we actually have development test units. So now we have the real flight software on those units in the loop, and our real FCOGs in the loop, our real timing in the loop, and now we kind of come through and see where any issues that we have in here. And we've kind of discovered some things through this where some interface issues, we've identified things such as, right now our big focus is on latency. So we have software timing model, latency model and StickSoft, but we've been using our big simulation to actually go in and induce events so that we can model the latency of the system on the actual hardware with the actual software to validate some of our performance metrics and validate our performance. So in terms of our approach, we kind of have this common approach where we iteratively make our flight software, we iteratively work with flight software for their review, their inputs to it, updates to that for our modeling simulation, and how we port that over to flight software for that operation. And one of our keys is this, that instead of us having to, as other approaches for smaller projects might take a different approach where you might have a GNC flight code that's kind of a level away from when you actually did your analysis. But in this case, all of our performance results are the same algorithm, the same pseudocode as what's being applied. So it gives a lot of confidence in what we'll be able to do for that. And through this iterative process with flight software in the loop, we're able to maintain quality and do testing and make sure we have all the requirements that when it goes to be Class A software, it's ready for that and it's able to easily become that through the processes and the rigor on our flight software group. Through a cross-discipline viewpoint, it eliminated a step for us having to basically write a document, feed it over, someone else implement it, and then go back and verify it. So that paper document step is gone now because we have the model we hand off full of documentation and test cases. So that helps to remove risk in where error-prone process of making sure that your software designer who doesn't know GNC might misinterpret something and we don't discover that until years down the road. Here we kind of have it already written out and defined and in a way that's easily able to be understood by the software designer of our algorithms for kind of better understanding. We do test analysis across the entire board for this as we're doing it through. Part of the way to do this was bringing in flight software architecture early, knowing what it did, how to integrate with them. So having our GNC and flight software teams kind of closely integrating and working together helped that a lot. So we have counterparts in the flight software and GNC side that we work very closely with in terms of all of our testing, reviewing results, developing code, and kind of make sure that they're all in the loop and understanding to what it's doing and how to approach it. And also enabled for this was having the tight CR on our side to manage our own code before we went out, so we understood what our changes were and traceability on our side. Some of our lessons learned from this is that it did reduce the requirements burden for what we need to do. That explicit thing was incredibly helpful to us, helped to understand any issues in implementation. As I mentioned before too, like we've found, some of our big lesson learned here, I'll go at the bottom, was that in terms of our interfaces. So we found an issue where a misunderstanding of an interface caused basically an interface swap where we didn't expect it to be. And so that kind of gave insight to if you go kind of this approach where you're providing flight software, it's also important to have requirements on the interfaces themselves, especially if you're real close to the hardware and say, we expect this message on this bus in this place in order for us to operate like we do, instead of having to check it in the back end of it. So having those requirements early on, defining hard requirements on inputs and outputs, is also incredibly helpful to manage those kind of risks. So part of our GNC model, like our new approach, kind of we had to kind of fit in with the way the sprints work, the way all the other processes work in flight software. But we have been able to work it out over the past couple of years. I think it's a pretty smooth process now, where we might be a little ahead of the next release of the flight software, but we kind of have worked out what that process looks like as we execute more and more. It's becoming a smoother process, in my opinion. And also for its components, as we go down to a lower level, as we're trying to model the software of other sensors, having good data there helped a lot to be able to provide that, having the data from the vendor in order to implement that. So for example, we have SCDs, some of our small lower level components that we model and have traceability to and validation to, and that helps us drive validation through our whole entire simulation process for that. And also another key item we learned from this was that use the right model where you need it. So for example, if you're doing software testing, your model needs to include the interface to a high level of detail. Whereas if you're doing performance-based analysis, that might not be as important, but it's more important to match the error, the sticks, the behavior of it. And so knowing what model to put where makes the most sense. So for example, like a interface model might not go well in a 6-off Monte Carlo sim, where we don't care about like a bus interface thing. We can model that at a higher level. Whereas you don't necessarily need high-level performance models that are exactly validated in your hardware loop platform because you're testing different things. So we've kind of seen those challenges, and we still have continually been improving both sides for better comparison between the two. So we can take our sim and their sim and basically do a cross shootout between our fully software 6-off and hardware loop 6-off on the other side. So there's been a lot of kind of lessons learned and things that we've done that have helped us kind of get a lot of insight into the flight software process, into what our code looks like, and eventually in order to be able to say that the GNC model as our design for our requirements works, and we have high confidence in that across the regime. So that's what I've got, and thank you very much, and I'll take any questions.
Questions?
What was your name? Oh, Evan Anslone. Yeah, so I am one of the 12. Yeah, so I am right here, Evan Anslone. I am SLS navigation. Naeem Ahmad is guidance. Young Kim is one of our DLEs for vehicle management. Paul Wonderpoint is flight mechanics. Jimmy Compton is our secondary DLE for this. Stephen Huff is controls. Thomas Parks Nav. John Wall is controls. And Christian Garcia is our big software integrator for GNC systems.
So I have just a couple questions to clarify what you were saying. First of all, what do you mean by executable pseudocode? It seems like an oxymoron.
Well, it's actually, so I mean, we hand over C code, but because we aren't a flight software organization, we don't have the rigor. We're not CMI certified. We technically cannot make flight code. It's a model of flight code, so it's pseudocode. So it's not, it's kind of a verbiage. It's kind of how we get around the requirements and the procedures, right? So we make code that's of quality, that is a model of what the code will look like in flight, but once it's gone through the rigor and approval of the flight software process, it's not actually flight software yet. So that's kind of why I'm calling it pseudocode.
But it's actual C.
Yeah, it's actual C code.
Okay.
It is,
So-
it is C code with inputs. We have a data file that has all the binary inputs you read out, binary outputs you can compare it to. So our unit test case basically says you take our C code, you wrap it, you run it, it matches what we did on our side.
Okay, and the second thing that I have is kind of goes with that, and that is when your model is essentially the behavior of your algorithms that you expect it to do. And with the flight code, if they make tweaks to make things work, then how does that propagate backwards to you? How do you keep those things in sync?
Yeah, so that's that CR process that we've got on here. So those kind of algorithmic things, they can't really, part of the agreement was they can't change it. Basically, they put a CR and say, you need to change this for this reason. They put a CR in, and then we go in and change it. So if it's a wrapper thing of how you interface with it, that's kind of managed on their side. But if it's an internal algorithmic thing, so say, for example, we have a 1 Hz guidance loop that won't run in our higher rate process, so we have to break it up. So we broke it up. That kind of thing came as a CR that said, hey, you need to re-implement this, do it this way. And then they formally gave us a CR, we accepted it, and we went implemented changes on our GNC model to account for that. So that's kind of how, if they see a tweak they want to make to it, it's supposed to go through this CR process back to us, and then we redeliver the next iteration of our model.
So they do their next iteration based on getting yours back forward?
Essentially.
Okay.
Yeah, so we'll deliver these models at regular intervals. So we have a verification level model, and then our last flight software drop was, I think, this spring. So our flight software is essentially done from the GNC perspective. So as they're doing testing and stuff, it goes through a very rigorous formal, like, we found this issue, this is what we want to change, and we kind of go through this whole loop over and over again.
Other questions?
If there was any change that you could make to the process, what would it be and why?
If anything, I would work more upfront on kind of making sure they understand, kind of sync up better with their sprint cycles on the site software development. Right now, we're kind of out of sync, and we kind of come, like, they'll come with a flight software release, say this date, and we'll come in 6 months early and develop our flight software. So I think tighter integration there and the processes could be useful, and better integrations between our teams and knowing when we release software to them and having that tighter role of be able to say, hey, we see this happening, can you change it quicker, and going on a quicker release schedule from our side. But that's limited because when we do a software release, we have to do Monte Carlo analysis and all this verification to make sure that we're still good. So that kind of limits how quickly we can move through this. It's similar with software, like, it's not just us going in, it's all kinds of other stuff happening, and so it's kind of, we're kind of beholden to when that date can happen from their stuff, because they're integrating so much more than just our little piece of it. Because we're just one little piece of the whole software piece, so we can't hold them up from what we're doing. So to make sure we're done early ahead of that to integrate in.
Other questions? Great. Thank you, Evan.
Right, thank you.